Welcome to Calculus BC. In today's episode, we're going to be learning Chapter 7.4, which is partial fractions. And what you need to understand about partial fractions is it's the notion of uncommon denominatorizing a fraction. And so if that doesn't make any sense to you, don't worry, it will, because you have done the reverse of what I just said before. You have done common denominatorizing a fraction. So we're just going to work that process in reverse. So why don't we go ahead and take a trip down memory lane, and we will try to add these two fractions together. So 7 over x minus 4 plus 4 over x minus 3. And we're going to just go ahead and try and simplify this expression here. And so if I wanted to get a common denominator here, the common denominator would be x minus 4 times x minus 3. And so what I tend to do here is I tend to just kind of write down the common denominator here. All right, so x minus 4 times x minus 3. And then what I look for is I look for what's missing. So what's missing from the left to get me that common denominator? Well, what's missing from the left is an x minus 3. And I got to do the same thing to the top and bottom. That way I'm not changing anything. And this will be an x minus 4 down here. So hopefully this all seems familiar. I will distribute the top and get 7x minus 21 plus, that's going to get me 4x minus 16. And so what that's going to get me is, if I can combine like terms here, since I'm already over the same denominator, that's going to be 11x and then minus 37. And that's going to be all over the original common denominator. So x minus 4 times x minus 3. And I apologize, I just realized I put an x minus 4 twice there. That should be a 3. Sorry about that. Okay, cool. So that is the notion of getting a common denominator to simplify a rational expression. Now, let's say, for example, let's pretend that we didn't know anything. Let's pretend that we began with the problem 11x minus 37 over x minus 4 times x minus 3. So now what I'm going to do is I'm going to split this fraction apart into two fractions. And I know it's going to be 2 because I've got two pieces in the denominator being multiplied here. So I'm going to go and say this is going to be x minus 4 here plus something over x minus 3. And what I'm going to do is I'm going to call this, I'm just going to call it A, and I'm going to call it B. Again, what am I doing? I'm trying to split this fraction apart. I'm uncommon denominatorizing. That's what partial fractions is asking me to do. Well, what I'm going to do is I'm going to go and get the common denominator here, and I'm going to say that the common denominator, again, is just that x minus 4 times x minus 3. And I'm going to go and multiply this guy by x minus 4 and multiply this guy by x minus 3. What that's going to give me is a parentheses x minus 3 plus b parentheses x minus 4 all over, again, that same denominator. So it's going to be x minus 4 times x plus 3. And that's going to equal 11x minus 37 over x minus 4 times x minus 3. Now, back when we solved rational equations back in integrated 3, we learned that once the denominator was made the same, we could just set the numerators equal to each other. So we could then say that 11x minus 37 is equal to a parentheses x minus 3 plus b parentheses x minus 4. Now, at this point, I'm going to write this problem down twice because there are a couple of ways we can go and solve this. Now, if by now I haven't made it clear, I apologize, but we are going to be solving for a and b. That's what we're trying to find. And the reason why we're solving for a and b and not x is because we're trying to find out what coefficient goes in the numerator of one of the fractions and then what other coefficient goes in the numerator of the other fraction. Now, we know what that is because we did this problem already. We should fully expect a to be 7. We should fully expect b to be 4. But again, we are operating under the pretense that we don't know anything. So I'm going to go ahead and split these problems down. Again, I have one version of how I'm going to solve for a and b on the left. I'm going to have a different version of how I'm going to solve for a and b on the right. And so the way I'm going to solve for a and b on the left is going to be more of a traditional thing. I'm going to call it ax minus 3a plus bx minus 4b. And I'm going to go and group the a things together. So I'm going to say ax plus bx minus 3a minus 4b equals 11x minus 37. So now from here, what I'm going to do is I'm going to do something called solving by association. So before I do that, I'm going to go and say 11x minus 37 is equal to, I'm going to factor out an x here, and I'm going to call it a plus b times x minus 3a minus 4b. Now, at this point, there's a lot of symbols on the board. However, remember, a and b are constants, right? Which means 3a is another constant and 4b is another constant. So if I combine those terms, I'd get another constant, right? The a plus b here is attached to the x, similar to how the 11 is attached to the x. What I have here is I have a linear equation equaling a linear equation. So I'm going to go ahead and set these pieces equal to each other. So a plus b would equal then 11, because that's the linear portion. Negative 37 would equal negative 3a minus 4b. That's the constant section. And what I'm going to do is I'm going to go ahead and set them on top of each other. I'm going to solve this. We're back in integrated 1. I'm going to solve it like a system. So negative 3a minus 4b equals negative 37. I'll go and solve for a first. So I'll go and multiply the whole thing by 3. So what I get is I get 3a plus 3b equals 33. And so now what I'm going to do is I'm going to go ahead and now add downward. I'm going to go ahead and cancel these guys out, and I get b equals, or negative b equals negative 4. So if I multiply both sides by negative 1, I get b equals 4. Now, is that what b equaled in the beginning? I think b did equal 4 in the beginning. I think we have a winner, so we're good. And so now I'm going to go and plug this into the next place where I can solve for a. So I'm going to choose the original of this guy. So I'm going to say a plus 4 equals 1. A plus 4 equals 11. And I'll go and say negative 4 on either side, and I get a equals 7, which I feel like we had before. So that's going to be right here. So a equals 7. Is that what that equals from the beginning? It did equal 7. Cool. So we've got this method of solving using a solve by association or a system. Pretty good, and I think it's important to know this skill. About 97% of the partial fraction problems, I tend to not do this method. It's a little on the slow side. What we have on this side, though, is I'm going to go and call this risky business, is what I call it. Kind of a decent movie also starring Tom Cruise. And I call it risky business, not that it's any risky. It's just, you just have to really be careful with your substitution. We have to keep in mind here that what we're doing is we're trying to solve for a and b, which means x is largely a constant here. And so that means I can let x equal whatever I want. So what I'm going to do is on this side of the problem, underneath the a, is I'm going to say let x equal 3. And what that does is it allows for the a portion to disappear and only the b portion to survive. So what I've got is b times, looks like, actually I'll write it over here. If I let x equal 3, I got b times, looks like 3 minus 4 would be negative 1, equals, and again, I let x equal 3, so that's going to be 33 minus 37. So negative b equals negative 4, so b equals 4 just the same. On the other side, I'm going to let x equal 4, because what that'll do is that'll let b go away. And then I've got, looks like if I let x equal 4, I've got 44 minus 37 equals, looks like a. So then subtracting those, I end up with 7 equaling a. And here we are. We're back to where we started. We've got 4 over x minus 3 plus 7 over x minus 4 after solving for a and b. So that's partial fractions for you. Now, if you're wondering, why would we ever want to know this? It's a great question. I can sense you thinking that right away. Well, the reason why partial fractions is important, I'll type this in. Why do we care about partial fractions? And why are we doing some seemingly non-calculus thing in a calculus BC class? Well, what happens when we uncommon denominatorize an expression, what it does is it allows us to see the integral expression, better. And so if I call that, let's say I start off with x squared plus, or rather minus 7x plus 12 dx. I could factor it. I could factor the bottom first. So 11x minus 37 up top over x minus 4 times x minus 3 dx. Now, via partial fractions, we just extrapolated that this expression here inside the integral can become 4 over x minus 3 plus 7 over x minus 4 dx, which is a pretty easy integral to have, because now you've got 4 times the natural log of absolute value of x minus 3 plus 7 times the natural log of the absolute value of x minus 4, and then plus c. And that is why partial fractions is learned, is when you have this odd-looking rational function that you feel like you need to split apart. Partial fractions becomes a part of your life where you have to split the fraction apart. You have to uncommon denominatorize it. That way you can integrate the pieces individually. So hopefully that makes sense. I'll be back with another example. Give me a second. So in this first example, we're going to be integrating a really odd-looking rational function. Now, if you look at this, the reason why I probably wouldn't do something like this to it. Now, ordinarily, this wouldn't be terribly bad of a maneuver. I could start off with this, right? But if you look at it this way, if you integrated that, you would assuredly get x squared minus 7x minus 8, to the what was it, to the 0th power over 0. I guess that wouldn't make any sense. You could do ln, right? You could do ln of x squared minus 7x minus 8. But unfortunately, the inside isn't linear, so it's not like we can rule chain out anything that's going on here. So I feel like this is going to be a pretty weird-looking rational function, which means I think partial fractions is going to be part of our future here. Now, I want you guys to have that intuition with partial fractions and not just think, okay, well, we're in the partial fractions section, so it makes sense that partial fractions would be part of it. But on the side here, I'm going to go ahead and split this fraction up. I'm going to say 1 over x minus 8 times x plus 1. Hopefully you notice that I did, in fact, factor the bottom. And I factored the bottom because I know this is going to be the result of some a over the x minus 8 and some b over the x plus 1. And so now I'm going to go ahead and I can bypass the whole common denominator step, kind of, and call it a parentheses x plus 1 plus b over x minus 8. Now, if you noticed, I put the x minus 8 in front and the x plus 1 on the right. Had you reversed them, it's no problem. So if you pause the video and reverse the x plus 1 and the x minus 8, everything works out in the end, because a is going to be the constant it's supposed to be, whether positive or negative, and we'll find that out in the course of the investigation. B is going to be it's going to be a constant, and it's going to be the one that we're looking for. So don't worry, everything resolves itself in these problems. So from here, let's take on some risky business here. So I'm going to go ahead and say that what we've got is we're going to say 1. So 1 equals this. So what I'm going to do is I'm going to say let x equal negative 1. What that's going to do is that's going to make the a part go away. Again, I'm doing risky business to solve for b and a. And if I let the a part go away, I'm going to get 1 equals b times negative 1 minus 8 is negative 9, which means b equals negative 1/9. Okay, cool. I'm going to keep him in my back pocket here. And then on the right side, I'm going to say, okay, well, let x equal 8. And if I do that, the b part's going to go away, and I end up with 1 equaling a times 9. So a equals 1/9. So how does that help me? Well, what it tells me is it tells me that the integral of this is really the integral. So the a is over the x minus 8. So I'm going to say 1/9 over x minus 8. And then since b is a negative 1/9, it's not going to be plus negative. I'll just call it minus 1/9 over x plus 1. And rather than integrating off the cuff, I'll probably just factor out that 1/9 because it'll make my life easier. So 1 over x minus 8 minus 1 over x plus 1 dx. And now there's going to be some natural log in my life. I'm going to say 1/9 natural log of x minus 8 minus natural log of x plus 1 plus c. And I just have to make sure that that 1/9 is being multiplied by the entire integral. And that would be it. Now, if you wanted to, you could start looking at logarithms a little bit differently, because the AP test probably won't give it to you all expanded out like this, but they might. It's very likely that they're probably just going to consolidate this thing more in an attempt to save ink on their, printability cost. they're probably going to call it x minus 8 over x plus 1 plus c. And then that way they can save up on the ink. They don't have to type as many ln's. Saves them a little bit of money. Every penny saved, a penny saved is a penny earned, I guess. So there you go. So that is this next one. Okay. So give me a second. I'll be on with the next one. Give me a second. In this example, I want to draw to your attention something odd that happens with partial fraction decomposition here. And that is that it's starting to look a little more complicated, right? We've got a quadratic up top with presumably a cubic on the bottom, and so that makes it partial fraction separable. So I'm going to go ahead and make this into a separating fraction here. So I'm going to go ahead and do x squared plus x minus 2 here, all over 3x minus 1. Again, I'm just going to do this on the side here. And I'm going to say that's going to equal a over, in this case, the order is actually going to matter because these terms are not both linear. So I'm actually going to call this plus something over x squared plus 1. Now, what I want to draw your attention to is notice the relationship between the numerator versus the denominator. The numerator always trails the denominator by one, what I call functional power. So what I mean by that is if you look at a is a constant. And that's because his denominator is a linear. Now, if you notice the second fraction here is quadratic, which means the top of this must be linear. So I'm not going to call him b because that would be constant. I'm going to call him bx plus c because he has to be some form of a linear function. So keep that in mind, that your functions will always have to trail in the numerator by one functional factor than the denominator, if that makes sense. And so now what I'm going to do is I'm going to go ahead and get that common denominator, and I'm going to go ahead and say that x squared plus x minus 2 is equal to a parentheses x squared plus 1 plus bx plus c parentheses 3x minus 1. Now at this point we have an option. We can probably do risky business on this one. It is a bit risky just letting x become something because it requires some fractional maneuvering, but why don't we go and give it a try? Risky business is kind of fun. And so what I'm going to do is I'm going to let x equal 1/3. The reason why I chose 1/3 is because 1/3 will make this entire piece go away, multiplying the entire thing here by 0, allowing me to solve for just a only. So what is that going to look like? Well, that's going to be a parentheses 1/3 squared is 1/9 plus 1. I'm going to call him 9 over 9. Again, I'm going to kind of work through this a little bit quickly here. And that's going to be 1/3 squared again. So that'll be 1/9 plus 1/3 minus 2. So now this is going to become 2/9. This is going to become negative 18/9. So what I have is 3/9 minus 18/9. So what I have here, whoops, not 3/9. What I mean is I have 4/9 minus 18/9, which is going to be negative 14/9. And that's going to equal a times, these guys will combine out to become 10/9. So I'll multiply the whole thing by 9 over 10. And the 9's going to cancel. I end up with negative 7/5. Negative 7/5 equals a. Keep that in my back pocket. I'll probably need it later. Okay, in the next little bit here, I'm going to go ahead and solve. I'm going to let x equal 0. Okay, and I'm choosing 0 because it's going to help b go away, and it's going to make the entire left side almost go away. The reason why I just choose numbers that I think are going to make the problem easy to work with. So that's why it's called risky business, because sometimes you have to choose numbers. It's a little bit of a risk. Sometimes you choose a number that's bad, you just back out and try it all over again. So let x equaling 0, that means that on the left side I'll have negative 2, and that's going to equal, let's see, that guy's going to go to 1, and we already know that a is negative 7/5. So you see how that's workable, right? and then plus b times 0 is 0, but all I have is c times, looks like -1 right here. And so what I get is I get -2 equals -7/5 minus c. What I'll do is I'll go ahead and multiply the whole thing by -1. While I do that, that'll give me a c plus 7/5, and that's going to give me a 2, but I'll go and call him 10/5 for a common denominator, so that when I subtract this guy over, I get c equaling 3/5. So now, we got to choose another number to make our lives a little bit easier. I'll go ahead and say let x equal 1. Why did I choose 1? Because it's what's going to allow the b to survive, and it's also a pretty easy number to work with. And so if I let the left side equal 1, or in other words, the x become 1 on the left side, I get 0, because that's 1 plus 1, which is 2, minus 2, which is 0, so that's great. So 0 equals, if I let x equal 1, that's going to become 1 plus 1, which is 2, and a was -7/5. We found that out a little while ago. And then that's going to be plus b times, again, we let x be 1, so we're going to call him 1 in here, plus c, well, c is 3/5. We found that out a little while ago as well. Times, 3 times 1 is 3, minus 1 is going to be 2. And again, our objective is to solve for b at this point. So what I'm going to do is I'm going to go ahead and multiply this in. I'm going to get -14/5 plus 2 parentheses b plus 3/5, and that's going to equal 0. I'm going to kick him over. I got 14/5 equals 2 parentheses b plus 3/5. Divide by 2, which is the same thing as multiplying by 1/2. I get 7/5 equals b plus 3/5. I'll go and subtract 3/5 from either side. And what I get is I get b equaling 4/5. Now, I've done a lot of math, but believe it or not, we haven't done any calculus yet. So now that I have my values for a, b, and c, now I can say that the integral, I'll go and copy him in because I want to make sure that we have this within context here. The integral of this is really the integral of, looks like -7/5 over 3x minus 1. And then that's going to be plus, let's see, bx plus c. So that's going to be 4/5 x plus 3/5. 4/5 x plus 3/5 over x squared plus 1 dx. Now what I'm going to do is, this guy's a binomial here. I'm going to go and split him up again. And I'm going to say the integral of -7/5 over 3x minus 1 dx. Actually, I'll keep him. Now I'm going to look at this as a binomial fraction. I'm going to split him up one more time. And I've got the integral of -7/5 over 3x minus 1 plus 4/5 x over x squared plus 1 plus 3/5 over x squared plus 1 dx. So now what I'm going to do is I'm going to split these up, and I'm going to give them each their own integral. And so what I'm going to do is I'm going to say this is -7/5 integral of 1 over 3x minus 1 dx plus 4/5 integral x over x squared plus 1 dx. If you see what's about to happen here, it is going to happen. Plus 3/5 integral 1 over x squared plus 1 dx. Now, of the three, this one on the right side is the most straightforward. This is going to be 3/5 times tan inverse of x. I'll slap on the plus c right there. This guy is the most involved. He is, yes, you guessed it, he is a u sub, where u is going to be x squared plus 1, du is going to be 2x dx, which means 1/2 du is equal to x dx. So you have your linkage there. So now you have 4/5 times 1/2 times the integral of 1 over u du. And then technically, the left guy is also a U sub, but I'm going to go and rule chain him out into ln of absolute value of 3x minus 1 times 1/3 for rule chain. Now, I still haven't integrated that blue guy in the middle yet. I'm going to do him right now. These guys are going to kind of cancel each other. I get 2/5 times the natural log of the absolute value of x squared plus 1. I technically didn't need the absolute value, but I'll keep them there anyways. Plus 3/5 tan inverse of x plus c. And then I'll go and multiply these guys out to become negative 7 over 15 ln of 3x minus 1. And then that's all being added together. Okay, so long integral right here, long integration process. But I wanted to show you that when you have a quadratic on the bottom, it has to be numerated by a linear factor up top. These ones do get kind of nasty. So hopefully that didn't traumatize you too much. I'll be back with the next thing we're going to do. Before getting to the next example, I do want to talk a little bit about duplication. And duplication is an exception to the rule I just talked to you about when it came to how a linear has to be on top of a quadratic has to be on top of a cubic, and whatnot. And so I'm going to go and set up a duplication problem for you. And it's going to look like this. 1 over, say, x minus 2 squared. So what I'm going to do here is I'm actually going to go ahead and tell you first off that this does not partially fraction out into x minus 2 plus b over x minus 2. The reason being is because the common denominator is x minus 2 squared, which means if we were to get a common denominator here, the common denominator is already set at x minus 2, but that's not being squared. So one of these actually needs to have a squared on it. That way the common denominator can be x minus 2 squared. So hopefully that makes sense. Now, when I go to break this thing apart, this would be the appropriate breakage of this. Now, I know what you're thinking. You're thinking, wait a second, didn't you just tell us that a constant over a linear is okay, but it's got to be linear over a quadratic? So why is this not bx plus c? And it's a really good question, and I will tell you that it actually is bx plus c, but everything gets simplified out into just becoming b. Allow me to show you what I mean by that. What I really have here is a over x minus 2 plus, I'm going to call this b, and let's just assume that it is bx plus c. I'll call it bx, and what I'm going to do is I'm going to go ahead and subtract a 2b, and I'm going to add a 2b to both to the expression. Now, what this does, and then plus c here. Now, what this does here is these guys cancel out to 0, so I end up with bx plus c, so there's no harm there. But what I'm going to do is I'm actually going to split this expression into a couple of different fractions here. I'm going to say a over x minus 2 plus, I'm going to call this bx minus 2b over x minus 2 squared plus 2b plus c over x minus 2 squared. So I just separated the fraction out. And then here I'm going to go and factor out a b from the middle expression. So I have a over x minus 2 plus b times x minus 2 over x minus 2 squared plus 2b plus c over x minus 2 squared. Well, if you notice, the x minus 2's are going to cancel each other out. And I end up with a over x minus 2 plus b over x minus 2 plus 2b plus c over x minus 2 squared. Well, we have to remember that a, b, and c, those are all constants, right? Only x is the variable. So if I combined these terms, because they already have the common denominator, I can say a plus b is equal to c, I don't know, some constant, over x minus 2. And then plus 2b plus c is just going to be some constant. I'll just call him d over x minus 2 squared. So either way I cut it, I have a constant over my linear factor and a constant over my linear factor squared as its duplication. So hopefully that makes sense as to why when you have duplication, you can just line them up as constant plus constant plus constant. Hopefully that makes enough sense. The reason why I bring that up is because of the last example that I'm going to give to you. Give me a second, I'll be right back. The last example I want to go over with you guys is the notion of the improper fraction. Now, as we can recall, an improper fraction is a fraction in which the numerator is larger than the denominator. And the reason why I bring this up is because when we decompose a partial fraction, it needs to be just that. It needs to be an actual proper fraction. And in the example that we see here, clearly that's not the case. The powers up top and bottom are the same. The coefficient with the x squared is 3 up top and 1 on bottom. So this is definitely going to be an improper fraction. So how do we deal with an improper fraction situation? Well, what I'm going to do is I'm going to initiate and bring back an old friend that will make its triumphant return. I am going to long divide the bottom into the top. And if I divide x squared into 3x squared, I'll get a 3. I get 3x squared minus 12x plus 12. And if I subtract the whole thing, this will go minus, this will go plus, this will go minus, and I end up with 12x minus 22 as my remainder. So how does that help me? Well, it gives me the integral of 3, right, which is what I divided out, and then plus 12x minus 22 over x squared minus 4x plus 4 dx. And this is the piece that I'm going to uncommon denominatorize. So on the side here, I'm going to do 12x minus 22 over x minus 2 squared. Hopefully you guys don't mind if I factor that a little early. And notice we have a perfect square trinomial on bottom. That's going to have some duplication. So I'm going to go ahead and say this is a over x minus 2 plus b over x minus 2 squared. Now, where the duplication gets a little tricky is the notion of finding the common denominator. The common denominator is x minus 2 squared here, which means in order for me to get the common denominator, well, the b already has it. So the a simply needs an x minus 2. And so when I take down the 12x minus 22, I simply don't just cross multiply the denominators into the numerator. What I get is I get a parentheses x minus 2 plus a solitary b. And again, why is b by himself? It's because the b term already had the common denominator, so realistically, I just multiply the top and bottom by 1. So now I'm going to go ahead and initiate some risky business here. I'll go ahead and let x equal 2. That's going to make a go away. And b being already by itself, I end up getting 24 minus 22, so that ends up becoming 2 for b. And I'll go ahead and now solve for a by letting x equal 3. So if x equals 3, I'm going to get a times 1 plus b, which we know to be as 2, equaling x times, so x being 3, that's going to be 36 minus 22. 36 minus 22 is 14. I'm going to subtract 2 from both sides, and I get a equals 12. So now I'm ready to integrate this expression because I have now partially fractioned this expression here. So what I've got is the integral of 3 plus, looks like a is 12, so 12 over x minus 2 plus 2 over x minus 2 squared dx. So now I've got 3x plus 12 times the natural log of x minus 2. And then this is really 2 times x minus 2 to the negative 2. That's not going to become a natural log. What I end up with is minus 2 and then x minus 2 to the negative 1 plus c. And that ends up being my integral for this crazy expression here. So a couple things to just keep in mind. One, long division when it comes to improper fractions. Make sure you have a proper fraction by dividing the denominator into the numerator, making sure that the power on bottom is larger than the power up top. With duplication, make sure you're careful with that common denominator. Don't make that mistake like many people do. And then you get your partial fractions all set. So that should wrap it up for partial fractions. Hopefully you found this video helpful. As always, please leave comments in the comments area or questions in the comments area, and I will see you all in the next episode.